Hi guys, we're group 17 and today we'll be presenting on the topic towards personalized learning in mobile sensing systems. So this paper is our introduction to Internet of Things and how distributed systems can be used to scale the concept of IoT. So this Internet of Things, as you guys may know, has been around for a really long time. It's been developed and it's still developing. So the idea to take it to the next level is has become to apply what the trend is use machine learning and deep learning techniques. And the idea is that that's already been done and that has been there for a really long time. So let's say someone asks you a question, you basically get a list of suggestions that you could send as replies. That's basically a machine learning prediction algorithm at play. And there are a lot of other things like autocorrect as well, which is basically working through a machine learning algorithm. But in terms of Internet of Things, what do we actually need here? So we want our devices and systems to feel more personalized to us, and we also want them to be more secure at the same time. And it turns out for these individual things, machine learning algorithms have helped in the past, and we can possibly use them to help both of them at the same time. So the idea is that before deploying a machine learning model, we need a couple of things. The first thing that we need is a good amount of training data. As you guys may know, machine learning is really data hungry, and the higher amount of data we have, the better inferences we can make. We also need a good model architecture because without a proper model architecture, we won't be able to make anything of the training data that we have. And we also need to identify what are our computational limitations, because that's where we decide what kind of model can we not go for. We basically get to know where we can host our models and where we can't host our models. So these are some things that we do need to know before we practically apply any algorithm like this. And as I mentioned, we need personalization. And the reason we need personalization is because we want a better user experience. If we have like a global classifier or a global model, we can often make the user experience much worse. So, say for example, I really like milk, but you're lactose intolerant, and the both of us get a push notification on our phone that says, "Oh, we have a 20% off offer on all milk-based ice creams." Well, that's a really good deal for me, but that's not relevant to you, right? And that reduces and kind of decreases the user experience for you. That's something that you wouldn't like. Also, this can be extended to things like autocorrect and autocomplete. So we all have personalized typing styles, and let's say I'm typing at different speeds within a different language, then I wouldn't want my particular word to keep getting autocorrected to something that other users usually wanted autocorrected to. Essentially, something that's personalized based on what my typing pattern is going to feel much more comfortable, and I'm going to want to use the device more. So personalization is a big thing, and we can achieve that with the use of a local model by hosting a machine learning model on that particular device, which basically uses training data from exclusive to that device. But some of you may argue that we might find the need of a global machine learning model as well. And we do, because even though we have our differences, there are some things that are common to all of us. And let's say that in terms of using our phone, even though we may use different applications, all of us share the common operating system. Well, I use the Android operating system, and I'm sure many of you might be using the Android OS as well. So the idea is that let's say that I download an app which tries to send some malicious content uh, my my operating system. If I basically identify that vulnerability and try to train a local classifier for this, I'm definitely making myself secure. But that is not what Android wants. Android wants all its devices to be secure, to be equally secure at the same time. So the better approach here is to send that particular data as feedback to the cloud. That particular data becomes training data for a global classifier. The global classifier eventually learns how to deal with these vulnerabilities, and in the next update, we have a better Android, better and safer operating system. So we mentioned a local classifier, we also mentioned a global classifier, but in terms of applying it anywhere, what do we choose? And we can choose between maybe like, having a global model and training it in all of users' data. But as we discussed, it's going to cause a lack of personalization if we need it. And it may lead to some privacy problems in case, let's say you share something like your keyboard or typing patterns and someone gets access to that particular global model, then they can easily make a keylogger and try to replicate your behavior and use your data and pretend to be you for malicious intent. So Clearly, a global only model might not work in all the scenarios. Let's say that we try to use a local model. So we're trying to use a local model where we're trying to train everything and trying to host it on a singular machine. However, this is going to be really computationally expensive because usually our phones are low power devices which can't have that which can't host that complex models, and they can't have that the huge amounts of training data that is available for global models. So all in all, we realized that there's no one size fits all solution for this. So I wanted an answer to this, and I didn't know what to think. So I thought to myself, why can't we use both? And it turns out we can, because a lot of people before us have actually tried doing the same thing. So this is an interesting study that we found out. Um, this is not an example in the paper, but we found that this to be really interesting because this was used for a real life case. So what's happening in this particular paper is that this paper takes in the input as X-ray images of the cardiothoracic region of patients, and they use an ensemble of 6 local classifiers and 1 global classifier to basically joint model the prediction probability through a fusion algorithm. The idea is that their proposed classifier architecture outperforms all the state of the art architectures on the particular data sets. And this is a sign that instead of having one classifier, we can always go for a hybrid of sorts and basically use 2 different classifiers targeting different types of data. That is what our paper does as well. Back to our paper though, our paper does not model the probabilities together, but it rather suggests a hybrid or a pipeline of solution. What we're trying to do is we're trying to make a classification, which is going to be a binary classification. We're going to separate class 1 and class 2 together. But the idea is that some users might provide 0 labels to you. The reason for this is that let's say that a user between 2 p.m. to 4 p.m. does not want any of his information shared. At that point of time, in order to respect privacy, you basically do not label that point of data. So the idea is that we do have a global classifier here, and we do have a local classifier here as well. The global classifier will act as a reference model for all the machines which are hosting the local classifier, and the local classifier is going to train on the raw sensor data available on the phones. So the main idea is this, that a local classifier on the individual phones is going to classify data. It's going to either classify it as negative, as positive, or it's not going to label it at all. What's being shared between the local and the global classifier are the parameters. There's no raw data that's ever being exchanged, and since that is the reason, we're not compromising on security ever. The low level computations are being made by the local classifier, and the global model is going to be retrained on all the parameters of the local classifiers. This way, the global model learns the general trend in all the local classifiers, and it also becomes the new reference to the phones as well. So this is the PLOS approach, which seems really interesting. And if you want to talk about the general idea so far, what's happening is that we're trying to learn from all the local models in a distributed way. We're never trying to exchange raw data here. The only information that we're exchanging are the parameters of the local and the global model. That's it. The local model is basically classifying on the individual data that's available to it through its sensors. And the global model is basically trying to model a distribution on similarities. And this is also going to be a reference for the local models. So the local models, rather than having to retrain from scratch, can take the global model as a reference, and they are allowed to deviate a little here and there based on what their training data is like.
Okay, thanks, AK. After we have the general idea of what PLOS is, let me introduce more details of this algorithm. And actually, the proposed PLOS algorithm is inherits the spirit of the support vector machine, which is called SVM, which is also a very classic machine learning algorithm. And the basic idea of this algorithm is to find out the hyperplan that can maximize the margin between the two labeled class, and so that they can do the classification task. However, because at the real-time application, they have some problems, as also AK has introduced. There may some problems like the data are not labeled, and also for SVM algorithm, it cannot achieve the effects that to find out the uniqueness of different data sets because they have some biases between different user data set. So for this, we propose the PLOS, and to solve this, we have to like find out the identify the commonness of the data set, and also we have to capture the individual characteristic of different data sets, and this is our main goals. And like the image shown in the slides, we can find out that the red arrow is actually the common set of the different data sets, and this is the global hyperplane. And by we find out the biases of the different user data sets, we can find out the different hyperplane for different data sets, like the green arrow, orange arrow, and the purple arrow. They actually have some little difference between from the global plane. This is how we can achieve the personalized. And how we achieve this is actually from like first one, we do the classification. We label the unlabeled data to the appropriate class, and then we will do the like to find the maximum margin. This is how the algorithm work. And to achieve this, we actually propose an optimization formula, and by solve this optimization formula, we can find out the planes for different data sets. And we have to maximize the margin of the global hyperplane, and also to minimize the differences between the global hyperplane and those of the users, so that we can find the commonness and also find the uniqueness of the data set. And for the optimization part, as it is a very, very hard optimization problem, we actually want to talk lots about the mathematical part, but I will introduce some key algorithm or some key steps in the optimization part. The first one is CCP process. This is actually a process that try to turn a non-convex problem into a convex problem. So in that way, we can find it out more easily. As the convex problem, we can find out the lowest point, and for the convex problem, we can find the highest point, so that we can get the optimized result. And we also apply the cutting plane process, which is a very useful strategy to find out the optimized result. And also, we also have applied to find out the dual problem of the optimized formula, so that we can solve it easier. It's also a very useful optimized strategy. However, the above is basically of the PLOS ideas, and we call it centralized PLOS because we upload all of the data to the server, so that the server will do the calculation. But in this way, it also has lots of drawbacks, like they may cause some privacy issues, and also they may, because of the bandwidth or the energy constraints, they may cause some issues like the latency or something like that. And also, if we upload all of the data and let the server to do the computation, actually the computation time may be very great. So to solve these drawbacks, we propose a better solution, which is called distributed PLOS. Then this algorithm actually combine a distributed spirit with the PLOS algorithm. The main differences between the distributed PLOS and the centralized PLOS is that the distributed PLOS add a ADMM process, which is the algorithm that try to separate the big task into small tasks and let the small tasks do individually. And at last, they will combine the tasks together to solve the problem. And for distributed PLOS, they haven't like to upload all their data to the machine. They only have to do the calculation at their own machine and only update the parameter is okay. So let me dive more into introduce more about ADMM process. We want to talk about like a mathematical process. We only talk about general idea of this algorithm. Actually, it is like a puzzle game achieved by lots of people. And for each people, they have a small part of puzzles. They only have to fix they finish their own puzzle and then combine it together is okay. So the flow process is maybe look like the first division and then work independently and then do some alignment and coordination. If they match perfectly, then it's okay. We find out a good result. But if we have to do some alignment or do some coordination, then we will do the integration. And finally, we will integrate it together. And this is the main process of ADMM. For the distributed PLOS, it has a lot of real-world applications. like a personalized recommendation system and also customized advertising. Like the image showing the slide, for different mobile phone, we have their own local search data or local search history data. We don't want to like upload all of this personalized information to the server because it may cause some privacy problem. With the distributed payloads, actually, we can do the calculation on my own phones, and we only have to upload the parameter to the cloud, and then let the cloud to use their parameters to upload the global model, and we will get our personalized model. And this is how it works like. And that's all of my part, and I will let my partner Zhenling to introduce more about the effectiveness of how this algorithm works well in some data sets.
Thanks for AK and Zihao to share with us why we need PLS and what the PLS is. So now I will focus on how the researchers do experiment to validate their ideas and the experiment result. So the researchers have tested the centralized PLS on 3 different data sets. It's body sensor data, smartphone data, and synthesized data. The task is to do the classification on whether a user is standing or sitting. And the authors use 3 different baseline methods to measure the performance of the PLS. The 3 baseline methods are all single and group. For all baseline methods, it's basically a global hyperplane on the data of all users. So it's used one global model to do the classification to classify whether a user is standing or sitting. So it's a centralized method because there is only one global model. And for single baseline method, it's basically do the support vector machine or k-means on each single users. For every single users, they have their own models, so it's a localized method. And for group baseline methods, basically the combination of the both. So first, we just group similar users together, and within that group, we do the global hyperplane. We use a global model within that group. And how do we group similar users? We use spectral clustering. For those of you who are not familiar with spectral clustering, you can treat it as a measurement to measure how likely to users. And these are the experimental results of the centralized PLS. So there are 6 charts and showing that the experiment results on 3 different data sets and in 2 scenarios. The 3 different data sets are stated as previously, and 2 scenarios are with labels and without labels. So as mentioned above, a user can provide labels. A user can also do not provide labels. So there are 2 scenarios. And we can easily state that under these 6 graphs, the PLS always performs the best. So we can come to the conclusion that in all 3 data sets and in 2 settings of with and without labels, our proposed PLS always performs the best among 3 different baseline methods. And the author also did experiments on the distributed PLS. The left 2 figures show that the difference of accuracy between the centralized one and distributed version of the PLS. We can easily tell that the accuracy between those 2 versions are very close. It's basically near the 0. And for the third picture, it shows the running time in the relationship when the user increase. So we can easily say that when the user increase from 10 to 100, the running time of distributed version do not increase very much, but the centralized version increase rapidly. And the fourth picture shows the message overhead of the distributed PLS when the user increase from 10 to 100. Similarly, when user increase, the message overhead do not increase rapidly. So we can easily come to the conclusion that the centralized version and distributed version of the PLS, the accuracy is very close. And when it comes to the computational cost and the communication overhead, the distributed one has advantage because it do not increase when the user increase. So we basically draw the conclusion that the PLS is a personalized learning framework on mobile sensing, and it performs very well in terms of the accuracy compared to three different baseline methods. And for distributed version of the PLS, it has two advantages. One is that it do not need to send the user's data onto the server, so it provides protect privacy. The second one is it's very efficient in terms of energy computation and communication cost, especially when there are a lot of users. So the last one is about the future work. So the future work should focus on more sophisticated classification model and do experiment on the asynchronous distributed system. Thanks everyone. That's all of our presentation.